Okay, so we are talking about constraint optimization. We have looked at a single equality constraint, and now we are looking at a single inequality constraint. Okay, so this is just from last time. So in the single inequality constraint, the problem that we have is a simple objective function x1 plus x2, and the constraint is the interior of the circle. And immediately I know not immediately, but graphically I can see the solution is at point A, and I'm asking how do I improve? I'm at some point x, I want to improve. And to discuss this, we came up with two possible cases. One is the point that I am currently at is either inside the feasible set. Second case is I'm on the feasible set boundary. So that was case one. When x lies inside, we said that this is called an inactive constraint, right? Because the inequality becomes strict. And you use first order Taylor's theorem, so you get an expansion for C2x plus s, and turns out that any small s will work, because you can, as long as s is small, I can maintain this inequality. And in particular, if I choose s like this in the negative gradient direction, I am bound to decrease my function value. So this was a good candidate, okay? And as we said, this is a candidate, not a unique thing. Any feasible descent direction will work as long as the magnitude is small enough, okay? Then we said, let's look at the second case, right? So second case is where the constraint is active. That means C2x is identically equal to 0, which means I'm at the boundary. Now when I'm at the boundary, we have both things to look at. One is feasibility, which came from this equation. Second is decrease. So here now, feasibility said that grad C2 transpose S should be greater than or equal to 0. So that is which shaded region over here? The blue shaded region, right? Grad C2 and S should be in the same half space, so that their angle is acute. Therefore, the inner product is positive or greater than or equal to 0. That is my blue region. Grad F transpose S less than 0. That means grad F and S should be in should have a greater than 90 relation. So that gives me the red shaded region. Finally, I'm left with a cone, which is this yellow shaded region, right? So this has given me a possible region in which I can choose my S to move forward. Remember, we are not currently talking about an algorithm. Okay, we'll talk about an algorithm once we finish all of this, but any S in this direction is roughly okay. So I think I moved it to the right. So the question that we asked here is, how do I move to a better position? And finally, the second question that we want to ask is, when should I stop? Or when is there going to be no improvement possible? So that's the question that we'll start by asking today. So when do we stop improving? Okay. So let's go case by case. Case 1, okay. Remember, case 1 was when I am inside the boundary. So what do you think? When will I stop moving? When do you think this whole process will not, I cannot move to x plus s? I'm in the interior, so it's very difficult for me to jump into an infeasible point. So I'm in the interior already. So the hint is, look at the potential expression I have for S. When will I stop moving? Exactly. If grad F is 0, then I don't really know which direction to move in. If grad F is 0, that kind of kills it there, right? So in the case of case 1, just to remind you, was C2x was strictly greater than 0. Okay. So we have no feasible direction if grad f of x is equal to 0. Now, remember when we made this, when we discussed the equality constraint, we had introduced a Lagrangian, right? And the idea behind introducing the Lagrangian was to make a kind of a one-to-one comparison between constrained and unconstrained optimization, right? So, in the language of the Lagrangian, how can I quantify case 1? So, remember the Lagrangian L of x lambda is what was it, f of x minus lambda c2x, okay. And what is the Lagrangian with respect to x over here? It will be grad f x minus c2x, okay. And in the equality constraint problem, we had found out that the signature for being at the optimum point was what? Gradient of the Lagrangian was 0. If I want to keep the same kind of analogy over here, what do I do? Can I still set grad L equal to 0 to capture case 1? It doesn't seem like it will work, right? Because it's only setting one term to 0, which is the first term. In case 1, grad f equal to 0 means I cannot improve anymore. So that's a signature for a stationary point. What else can I do? Can I impose one additional condition so that grad L equal to 0 still captures the case? Grad C is not in my hand. Lambda is in my hand. So if I set lambda, so this was lambda 2. If I set lambda 2 equal to 0 in, right, then this condition seems to work. I can say that if I am in case 1, then two things have to happen for it to be a signature of a stationary point. Grad L equal to 0 and lambda 2 equal to 0. Okay. It seems very silly, like artificially I'm adding in this thing, and you know, but we'll see what is the power of doing that in a few moments. Okay. Now let's move to case 2. Case 2, when is case 2 not going to work out? If there is no intersection between these two half spaces, right? That's what we need to capture, okay? Now let's look at this a little bit geometrically once again. Let's look at this point over here. Sorry, I had used another color over here. Let's look at this point over here, A, okay? And this point was marked C, this point was marked B, and this point was marked D, right? At this point which I have chosen, obviously there is the yellow shaded cone, which is okay. Let's look at point A, which is the solution, okay? Now at point A in the solution, maybe I should draw this once again over here for clarity, okay? Which way is grad f pointing? At all points, grad f is always the same, which is 1, 1, right? So my grad f is here, my grad f is here, this is my grad f. What way was my grad C pointing? Grad C2? Outward or inward? Inward, right? Because I had defined C2 with a 2 minus x1 square minus x2 square. So grad gave me minus C1, minus 2C1, minus 2C2. So that makes this is my grad C2 and this is my grad C2. This is grad C2, okay? Now let's look at this point over here. So grad f transpose S should be less than 0. That means where am I? Here. Oops. Okay. Great is. And grad C2 transpose S should be greater than 0. That means where am I? here. Is there any intersection? There is no intersection. There is no intersection. The inequality is strict. Grad f transpose S is strictly less than 0. There is no intersection, right? So these together seem to be capturing it. So is there a relation that I can catch between grad f and grad C2? What can I say? In this situation at point A over here, is there a relation that you can observe between grad f and grad C2? It's staring at us in the face. What is it? They're parallel. Okay, so at this point I can say that grad f x star is equal to grad C2. This seems to work at point A. And what? Okay, so we'll come to that. Let's look at the same thing for point C over here. So this is point C. At point C, I have once again, let's look at this gray shaded region is going to give me grad f transpose S less than 0. I'm here. Grad C2 transpose S, where is it? Grad C2 transpose S should be, right? So in this case, I'm going to have something like this, right? That means, is there an intersection possible? The whole half space is possible. And we know that C is not a legitimate, is not the solution. In fact, this is the maximum of the problem, right? So now looking at this, how can you make this expression over here? How can we fine tune it just a little bit more? Lambda 2 should be greater than equal to 0. If I say lambda 2 greater than equal to 0, it captures point A and not point C. Okay, so lambda 2 greater than equal to 0 captures A correctly. Okay. Now, in terms of the Lagrangian, how do I write this? Remember, Lagrangian was f of x minus lambda 2 C2 of x. Now, I want to capture this case using the Lagrangian. What is the first thing I can say? I want to capture this condition. How do I capture it? Grad L with respect to x, this, if I set it equal to 0, it captures this, and lambda 2. So in case 2, this is what I have. In case 1, you have seen what we had. We had grad L equal to 0 and lambda 2 equal to 0, right? So this looks a little tedious to have these separate cases each time, right? So it turns out if you just stare at both of these cases a little bit more, you can come up with a very elegant way to combine them. So let's do that. So let's okay. So let us say what is the common thing between both of them? Grad L with respect to x is 0. So let's write that as the first condition because that's clearly common over here. Grad L x lambda star star is equal to 0. This is common to both cases. Okay. But we also need over here to catch case 2, let us say lambda 2 greater than equal to 0. This is needed. The second condition is interesting. The second way to combine it is quite interesting. Okay. It says, and have a look at this. That lambda 2 times C2 is equal to 0. Okay. So does this work for us? In case 1, what did I want? Lambda 2 to be 0, right? So this guy equal to 0 captured my case 1, right? Did this constraint cause any problem for us? It doesn't cause a problem because greater than equal to 0, the equal to part is getting set over here. What about case 2? C2 is 0 in case 2, so this is equal to 0 in case 2. That means in case 2, I don't have to force lambda 2 to be equal to 0. Lambda 2 can be some number greater than equal to 0. It is consistent because C2 equal to 0 is capturing it. So you notice this is quite clever, right? I have combined I've combined both cases. Now I don't have to talk about case 1, case 2. I say that these are the two conditions necessary for sufficing as a check for a stationary point. Grad L equal to 0, the Lagrange multiplier is greater than equal to 0, and lambda 2 C2 equal to 0. Okay. So this second condition turns out it is used so often in optimization, there is a name given to it. It's called the complementary condition. Complementarity. Okay, it's very, very central to constraint optimization. Okay, so let's just quickly summarize. Case 1 was set gradient of Lagrangian equal to 0. That seemed a little superfluous because what do I do with lambda 2? So I set lambda 2 equal to 0. I'm done with that. Case 2, what did I have to do? I basically had to set, along with the Lagrangian equal to 0, I had to set the parallel condition. Anti-parallel did not work, right? So this was the parallel and this was anti-parallel. This was for a negative lambda. This did not work, right? So that's why we had to force lambda to be greater than equal to 0. And then the nice way to combine these two is over here. It looks similar to unconstrained optimization now. It's just that way. Earlier in unconstrained, I had grad f equal to 0. Now I have grad L equal to 0 with now a few extra things. Lagrange multiplier greater than equal to 0 and complementary condition. Okay. Notice one very big hole or gap right now. I have not proven any of this. I'm just going from geometric intuition to formulating this. So we'll come to proofs later, time permitting. Okay. But the intuition from geometry, I hope, is very clear how we have arrived at this. There's a proper rigorous proof behind all of this, which we can come to. It's an AND. And you can see they don't contradict each other. So let's look at it again. In case 1, I needed lambda 2 to be equal to 0. It was an inactive constraint. So C2 is greater than 0, but I needed lambda 2 to be equal to 0. So case 1 is covered. And case 2, the constraint is active, C2 is 0, lambda 2 can be anything. So it's captured over here. But that is why the lambda 2 greater than 0 is included in the first case, in the first statement. Because the first statement is saying grad L equal to 0, that means the gradient of the function and the gradient of the constraint, they are parallel or anti-parallel, both are possible. So I additionally specify lambda 2 greater than equal to 0 to make it such that they are parallel and not anti-parallel. So this very simple analysis with a single inequality constraint has given us this complementarity condition. In the case of equality constraint, we never needed this complementarity condition, right? So later on as we go, we will talk about a general situation where I have equalities and inequalities. Together we'll formulate one big hefty theorem which tells us what are the first order necessary conditions for constraint optimization. But all the nuts and bolts are here itself. As you can guess, in the case of equality constraint, did I have a condition that the Lagrange multiplier should be greater than or equal to 0? No. Right? So that is what will turn out in the final theorem statement, where I have a combination of equalities and inequalities. The equality related Lagrange multipliers can take any sign. The inequality related Lagrange multipliers must be greater than or equal to 0. And I have this complementarity condition. This is together going to form our sort of canvas for doing constraint optimization. The first, you mean this guy? So this captures both case 1 and case 2. So let me put them side by side. So look at this. This is over here, case 1 is happening over here, right? So case 1, I can grad L equal to 0 is along with lambda 2 equal to 0. So both of these, let's call these statements, both of these statements together work for case 1 and case 2. The only difference is when I say lambda 2 C2 equal to 0, there are Either lambda 2 could be 0 or C2 could be 0 or both could be 0. So let's leave the third case aside. So either lambda 2 equal to 0, that is my case 1, along with statement 1. C2 equal to 0 along with statement 1 gives me case 2. That's how we do it. Okay. So I've combined it in a slightly neat way.